Today will be a part 2 of our Qiskit application module demo session. Last week we have the Qiskit optimization and Qiskit machine learning, and this week we have a Qiskit Nature and finance demo session with Max and Julien. So thank you, Ram. I see many people are tuning in now, and I see people are from India, Philippines, Mexico, and Ukraine. Just let us know in the chat that where you're tuning in from today. So I'm Julien from, I'm quantum developer advocate from the IBM quantum community team based in Singapore. So yeah. And for the first part, we will have a Qiskit Nature presented by Max. And Max is a predoctoral researcher in the Quantum Application Technological Group in IBM Research Zurich. He holds a BSc and MSc in Computational Science and Engineering from ETH Zurich. And he also followed multiple years of undergraduate chemistry study at ETH. He's currently working on his PhD thesis on methods and implementation of mixed quantum classical approaches for quantum computing under the supervision of Dr. Ivano in the IBM Research Zurich and Professor Luke Hutter in University of Zurich. He's also actively involved in the development of Qiskit Nature, the Qiskit's natural science-focused application module, which is what he's going to show us today. Welcome, Max.
Thanks a lot for the introduction. Hi, everyone. As June has nicely said, today I will be introducing Qiskit Nature with a quick demonstration. And as you may guess from its name, Qiskit Nature is the applications module that deals with all problems related to natural sciences. So that includes chemistry, physics, and biology. And today, rather than covering all of these branches, I will take a very specific deep dive into a chemistry-specific problem. And this is especially interesting because quantum chemistry poses a very natural simulation target for quantum computing. And I would like to put that into the words of Matthias Treuer, who said that if you have 125 orbitals and you want to store all possible configurations, then you need more memory in your classical computer than there are atoms in the universe. And this very nicely shows how difficult quantum chemical simulations are actually to treat on a classical computer. And to visualize that a little bit more, here on the right-hand side, I'm showing you some of the orbitals of a pyridine molecule. And this is just a subset of the orbitals, but in a very minimal description of pyridine, you already have more than 30 orbitals, which already gets you a quarter of the way to this limit that you will never be able to simulate on a classical computer. And pyridine is a small molecule. It only has 11 atoms. And what we are interested in are metal complexes or proteins, which easily have hundreds to thousands of atoms and even considerably more number of orbitals. And that just shows you how important it is that we can simulate such systems using a quantum computer. Because on a quantum computer, we really only need 250 qubits to represent these 125 orbitals. And while it is true that we're not close to having 250 qubits available today, we hope to have that available within the coming years. And that's why it's important that we already research and develop new quantum algorithms to simulate such systems today, so that we're ready once we have such quantum computers available to us in the future. And with that in mind, I would like to show you what we're doing in Qiskit Nature, what we have available now, and take you on a tour through its entire program stack. To start off with a short overview, I would like to quickly present you what we have available right now. And on the left-hand side, I'm showing you some of the solvers that we have available. We have some ground state calculation solvers, excited state calculation solvers. We have some Bopp assemblers, which allow you to investigate the potential energy surface of a molecule. We can calculate vibrational spectra, and we can also do thermodynamics. And all of these take as inputs so-called drivers, because we always rely on a classical pre-calculation to perform some very efficient computations of the coefficients that we need in order to actually represent our problem on the quantum computer. And I will get into the details of all of this in a second. But rather than trying to cover the entire breadth, we'll now go in depth onto the ground state calculation of a water molecule. So the general structure in Qiskit Nature is that there are three parts. You have a problem, that is the problem, whatever you want to simulate. You specify a solver, that is the means to how you want to solve a problem. And then this will return you a result that you can then investigate. And in terms of code, this is rather straightforward because you can simply write your result is the return type of the solve method on the solver given a certain problem. And this modular approach really allows a lot of flexibility and reusability for multiple solvers and multiple problems. Now, depending on the situation, the internals of a problem may look a little bit different. So for the purposes of today, we will be looking at the electronic structure problem. This problem takes an electronic structure driver, as well as some base transformers. The electronic structure driver is what I mentioned before. It's the interface to a classical code. So this is really at the core, which returns the coefficients that you need in order to represent your problem. It will return a so-called grouped electronic property, which is, as you may suggest from its name, a group of electronic properties, including the Hamiltonian of the system, dipole moment operators, the number of particles, the angular momentum, etc., etc. You can then also use several transformers in order to change your problem's nature. You can change a little bit the size of the problem in order to only look at a subset of it. And you can apply multiple such transformations if you want to, before then finally getting to a list of fermionic operators. And these are operators which are the interfacing step between the problem and the solver. Today, we will be using the ground state eigensolver, which finds the ground state of our system. It takes as an input two objects, a qubit converter, which deals with mapping our fermionic op into a qubit operator. And then it takes a minimum eigensolver, or a factory of an eigensolver, which then takes the qubit operator and actually applies the quantum algorithm to find the minimum eigenvalue of this operator. And in the end, you will get an algorithm result, which is exactly the return type that we were interested in. Now, before going into the actual code, let's talk a little bit about the theory behind electronic structure problems. What we want to do when trying to determine the electronic structure of a molecule is we want to find the eigenvalue of the Hamiltonian of our system. And this Hamiltonian consists of multiple objects. We have an electronic kinetic term, which describes the kinetic energy of our electrons. We have a potential term, which describes the interaction of our nuclei at the cores of our atoms, and the electrons, which is an attractive force. And then we have the electronic interaction. And there are actually two kinds. There's the Coulomb interaction, which is the repulsion of equally charged electrons. And we have the exchange interaction, which is just the interaction of exchanging two electrons with each other. And trying to find the eigenvalue of this Hamiltonian is rather easy because it means we have to solve the non-relativistic time-independent Schrödinger equation. That's quite a mouthful, but all it is this simple eigenvalue equation where we have our Hamiltonian, we have an eigenvector psi n, we have an eigenvalue en, and then the eigenvector again. And we're particularly interested in the ground state energy, and that's the eigenvalue which has the lowest energy, the lowest value. And this simply amounts to trying to find this, trying to solve this system. And the way that we would do that on a quantum computer is we try to find a good description of our ground state wave function, which is this eigenvector, in order to determine the eigenvalue. Now, I have to take a little bit more of a step into the theory because what we're actually using is so-called a second quantization notation. And that's just a different notation for rewriting our Hamiltonian. And as you can see, you again have a sum of terms, but this time you have these weird-looking operators, which are simply creation operators and annihilation operators of electrons. And you then have simple coefficients on these terms, the HPQ ones being the one-body integral terms, and the GPQRS being the two-body electronic integral coefficients. And these are the coefficients that we compute classically using the driver. And the reason we want to use the second quantization notation is because it allows us to represent the Hamiltonian and the state of our function in a uniform way. And that's a so-called occupation number vector formalism. So what I'm showing here on the right-hand side is 5 example orbitals, 3 of which are occupied and 2 of which are unoccupied. And if the lowest lying ones are occupied, this is the ground state. And we can now apply a annihilation operator on the 3rd orbital and a creation operator on the 4th orbital to create an excited state. And now all of a sudden we have an excited state, wave function representation, where we have hopped one electron into another orbital. And we can apply that multiple times in order to create doubly excited state functions. Now, using this formalism, we can actually represent our system very nicely also in the code. So what we'll now look at is the electronic structure problem. So first of all, we need the system that we actually want to simulate. And as I mentioned before, we want to simulate a water molecule for today's purposes. So we use the generic molecule interface, which takes a few input parameters. The first one being the geometry, where you have the atom kind. You have an oxygen atom and 2 hydrogen atoms. And then you have the coordinates of your system, which are simply the x, y, and z coordinates in Cartesian space. You have the multiplicity of your molecule, which just determines the number of unpaired electrons. So it's a different representation of the spin. And you can also specify a charge of your molecule if you have a charged system with additional electrons in it. But for today, we have only paired electrons. So all of them all molecular orbitals are doubly occupied, and you have no charge on the system. In the second step, we actually need to construct the driver. And for this, we're using the very generic electronic structure molecule driver, which takes the molecule which we have just constructed. It specifies the basis, which I will get to in a second, and it specifies the driver type. And there are various driver types available in Qiskit Nature. Here, we're using the PySCF driver, which is a commonly used classical code to simulate electronic structures. And it's also implemented in Python, which makes it very easily interfaceable with Qiskit. Now, we could simply run this driver and obtain a result from it. But in order to integrate it better into the rest of our stack, what we will do is we will actually wrap this into a so-called electronic structure problem. And the easiest way to do that is simply to pass the driver to this problem class, and then we have a problem instance. Now, out of curiosity, let's look at what the Hamiltonian actually looks like. So what we can do is we can call the second QOps method of this problem. This will return a list of second quantized operators. And the first entry of this list is actually the Hamiltonian. And we can investigate this Hamiltonian, and then we get this output at the bottom, which is truncated, because as you can see, there are actually 1,085 terms in this Hamiltonian. So this is quite a large system. And you can also see the register length being equal to 14. This tells us that once we map this Hamiltonian naively into a qubit operator, our operator will have 14 qubits. We can talk about that in a second because we can actually reduce this number. But for now, let's also look at the actual output here. So we can see that there is a list. We have a coefficient in the front, which is mostly real valued. Actually, all of these are real valued. So the complex phase is always 0. And you then have this notation at the back, which is the creation and annihilation operators with a given index. So we have a creation operator applying on index 0 and one applying on the index 1, as well as 2 annihilation operators applied on indices 2 and 6. And then so on and so forth. And there are 1,085 terms in here, so you can imagine this list being quite long. Now, we can also check even more properties which are contained in this problem. And that's by inspecting this grouped electronic property, which was internally returned by the driver. And we can investigate that by printing the group property of the problem, where we get actually a huge number of information. So first of all, we have the driver metadata, which tells us what driver we have used. We get an electronic basis transform, which allows us to transform between the atomic and molecular basis set, which I will get to in a second. As you can see, that is quite long. And we get some additional operators. So there's the particle number operator, which tells us, again, the 14 spin orbitals in our system, as well as the number of alpha and beta spin electrons, and the occupations in which orbitals these are situated. So we have 5 alpha spin orbitals. We have 7 in total, and 5 of them are occupied, and the same in the beta case. Then we have the electronic energy property, which is the one that we just investigated, being the Hamiltonian of the system. And then later on, we get also some electronic dipole moment operators, as well as operators to evaluate the angular momentum and the magnetization. Then finally, in the end, you also have the molecule, which we specified as an input in the beginning. Now, 14 qubits is actually quite a feat to simulate. So what we can do instead is we can actually decide to only look at a subset of the orbitals in our system. And this concept is known as an active space. So what I'm showing here on the right-hand side are a very abstract representation of orbitals, the solid lines being ones which are occupied and the dotted ones being ones which are virtual or unoccupied. And let's say we only want to map this blue box onto the quantum space. We can actually further say that all these occupied ones we can ignore just because we make an approximation and say that, okay, these are not going to interact with the higher lying orbitals. And what we can then do is we can actually perform a classical pre-processing step, which calculates an effective Hamiltonian, allowing us to only represent these 3 chosen orbitals on the quantum system and leaving the others to only being treated on the classical computer. The theory behind this is quite involved, but that's not what we're here for today. We're here for code. So let's look at how that works in Qiskit Nature. And for that, we have the so-called active space transformer. This is one of the base transformers that you can add to your problem. And the interface is very generic and very simple. So you have the active space transformer. It takes 2 inputs, the number of active electrons, which we can set to 2, and the number of molecular orbitals, which we can set to 3. This is exactly the example from before. And we can now construct a new electronic subscript problem. I'm calling it problem reduced to state that it's a reduced size. And here we again pass in the driver as the first argument, but also a list of transformers as the second argument. And we can now again look at the Hamiltonian. And what we will see is that now the register length is actually only 6 instead of 14, which matches the 3 molecular orbitals mapping to 6 qubits. And you can also see that the number of terms has greatly decreased. So now there are only 33 terms compared to the 1085 that we had before. And you can also look at the grouped electronic property again, this time the transform version, which essentially contains the similar output to before. We have the basis transforms. We now have the reduced number of particles in our system. And we have the Hamiltonian, the dipole moments, etc., etc. Now, I already mentioned a few times that I was going to come back to this basis set that we were looking at. So what is that actually? So what we've introduced is the so-called molecular orbitals. And you may know from your high school chemistry class that each element in the periodic table has a certain number of atomic orbitals or shells. So for example, the oxygen atom has a 1s, a 2s, and a 2p shell, whereas the hydrogen atom only has a 1s shell. And when we simulate the system, we somehow have to represent this. And that's what we use atomic orbitals for. And each atomic orbital consists of a certain number of functions that we combine linearly. And these functions are given by the basis set of our choice. Earlier, we chose STO3G, which is a very minimal and very crude approximation, but it works well for simple demonstrations. And what you then have is when you actually want to describe the molecule and not only the atom, you combine all the atomic orbitals in your system linearly to generate a new set of molecular orbitals. So in other words, the molecular orbitals are simply a linear combination of all your atomic orbitals. And that also means that you actually have the same number of atomic orbitals as same number of molecular orbitals as atomic orbitals. So this is really just a unitary transformation from one basis into another one. And in Qiskit, we are working with so-called spin orbitals. And that's simply the fact that each molecular orbital can have an upspin and a downspin electron. But a spin orbital is then simply either of those cases, right? So for each molecular orbital, we have 2 spin orbitals. And when we now want to map this onto the quantum computer, we can choose different mappings. A very simple example being the Jordan-Wigner mapping, where we can map the occupation of a given spin orbital onto a single qubit, in this case represented as a spin. So each spin orbital will be mapped to a single qubit, and that's why we have this one-to-one correspondence in the case of the Jordan-Wigner mapping. This, in terms of code, is also very simple. We need 2 concepts here. We need a qubit converter, and we need the Jordan-Wigner mapper. And we simply pass the Jordan-Wigner mapper into the qubit converter, and we can then tell this converter to convert a given Hamiltonian. In this case, I'm using the reduced Hamiltonian, which had length 6. And this will return us a Pauli sum up from Qiskit Terra. And if we look at this operator, we can see that we again have a weight and a Pauli term, and this continues for a while. So there's just a weighted sum of Pauli terms. At this step, we can again apply some reductions to our system by using different mappings, which are a little bit more elaborate. The most common example being the parity mapping, which doesn't map the occupation of an orbital to a qubit, but instead the parity of an orbital to a single qubit. And what this allows us to do is, due to symmetries arising in this mapping, we can reduce 2 qubits, and that's something called the 2-qubit reduction. And as you can see, when we apply this, we simply construct a different qubit converter with the parity mapping. We enable 2-qubit reduction by setting this argument to true. And we can then convert the Hamiltonian that we had before again, but this time passing in the number of particles that we can get from our problem. This is important because the qubit that we can remove depends on the number of particles in our system. And now, investigating this qubit operator again, compared to the one before, we only have 4 qubits compared to 6. So this really is the exact, this will result in the exact same eigenvalue. It's just simpler to simulate because we require fewer qubits to simulate the system. Note that there's an artifact here that we have some complex phases, but all of these are negligibly small. So on the numerical precision, these are identical to 0. Now, we have defined a problem. We have mapped it into the qubit space. Now it's actually time to find the ground state solution. And for that, we can use a quantum algorithm. So the ground state solution is simply the one eigenvalue, which is the lowest value in itself. So we have the ground state wave function, which is simply the state vector of our system, and the corresponding eigenvalue. And because this is the lowest one in energy, we can apply a so-called variational algorithm. And the variational algorithm does nothing else but try to find the best description of this wave function with the target of minimizing the eigenvalue of a given wave function. And one example of this is the variational quantum eigensolver. And here I'd quickly summarize the idea. So we had the fermionic Hamiltonian that we looked at in the very beginning. We mapped this to a qubit Hamiltonian, which is a weighted sum of Pauli terms. And the way that the VQE works is then we prepare a trial state called psi, parameterized with theta, which is a set of parameters. And then for each of these Pauli terms that we have in our Hamiltonian, we measure the expectation value at the given trial state. We can return all of these expectation values to the classical computer in orange, which then calculates the energy by evaluating this weighted sum, which is given by the qubit Hamiltonian. And because this is a variational algorithm, we know that this energy is always greater or equal than the exact physical energy of the system. And this means that we can then adjust the parameters theta of our trial state, and then do this in an iterative loop with the target of minimizing the energy that we get in this as the result of this weighted sum. And in doing so, we can then converge the description of our trial state and find a solution in terms of the optimal parameters. And this will give us the optimal trial state, which will then give us the ground state solution. In terms of code, this is very simple. What we have in Qiskit Nature is actually a so-called VQE UCC factory. This is a factory class wrapping the VQE algorithm implemented in Qiskit Terra. And the reason we have this as a factory is that it allows us to construct this UCC ansatz, which is inspired from a classical code. It allows us to construct this later on in the stack because otherwise it would require the number of particles as an input, which you may not know in the beginning when starting the simulation, because you may want to apply some reductions which change this number. So using this factory, we can postpone the construction of this ansatz. And the factory has some simple arguments. First of all, we have to pass in a quantum instance. This, for the purposes of this example, here I'm using the state vector simulator, which is an exact simulation of a quantum computer. There's also the QASM simulator available, which includes sampling noise and also allows you to simulate noise of gates and qubits. But today, we're not going to use that. And then we can also specify an optimizer, which here I'm just using an SLSQP optimizer, just to show you that there are additional parameters here. There are even more parameters, but you can have a look at the documentation online to find out what these are. Now, this factory we can then pass into the so-called ground state eigensolver. So we can import the ground state eigensolver, we give it the qubit converter. Now I'm using the one with the parity mapping, and we give it the factory. And now we can do what I showed in the very beginning. We can construct the result, which is simply by calling solve on the solver and passing in the problem that we want to solve. And this will produce a result, which we can then print. And here we can get an output where we see the ground state energy has been computed, which consists of multiple parts. We have the electronic ground state energy. There's a computed part to it, and there is an extracted energy resulting from the active space transformer that we have applied. On top of the electronic ground state energy, there's also the nuclear repulsion energy, which was computed by the classical PySCF driver for us. And adding these two together will give us the total ground state energy of our system, which is minus 74.96 Hartree. We also get some additional information about measured observables, like the number of particles, the spin of our system, and the magnetization. And we also get some dipole moments, which are evaluated, which I will not go into the details of now. Instead, I would like to take the last few minutes and talk about VQE Runtime. This is a new feature which we have added in the IBM Quantum Experience, and it allows us to greatly improve the performance of running VQE simulations. So before we had the VQE runtime, as a user, you would run a VQE locally, you would send the circuit jobs to the quantum device via the IBM server, where you would have to wait in a queue with all the other people that would also want to simulate some quantum circuits. And once the circuit execution ended, it would return the results to you, and then you may have to do that again. Today, with the VQE runtime, what you can do is you can actually call a remote VQE on the IBM server. And that allows us to greatly reduce the time that you queue, because you only queue once to start the VQE, and then you can, the IBM server can quickly communicate with the quantum device directly, perform the circuit execution, and once it has finished, it will return the results to you. And as a quick example here on the right-hand side, I picked an old slide where we simulated a lithium hydride molecule using a very simple ansatz. And in the traditional way, before we had the VQE runtime, you would have to wait, or each iteration would take on the order of 115 seconds, so that being the median. Using the runtime, the median went down to 21 seconds. So you can see this is a very significant performance improvement. Now, the way that you use that in Qiskit Nature is also very simple. But before doing that, I quickly want to also show you how you can construct an ansatz manually. So before we use the VQE UCC factory, which constructed an ansatz for us, but there are also other ansatz which you can use. And here I'm picking an example from the Qiskit Terra library, the circuit library, which is called Efficient SU2. And it simply takes the number of qubits in your system. You can specify the type of entanglement. And when looking at this ansatz where we have a linear entanglement, you can see that we have 4 qubits, which all have some rotation gates at the beginning and the end. And in between, we have a linear entanglement of all these qubits. Using this, we can then step into actually running a VQE runtime simulation. So first, you will need to have an IBM Q account, which you can create for free on quantum-computing.ibm.com. Once you have loaded that, you need to load that account. You can store the credentials in your Python environment. So load account will only work once you have actually stored an account previously. And you then have to do 2 steps. You need to get the provider. Here I'm getting the open provider, which has runtime support, as you can see down here. And you then need to get a backend. And there are multiple backends available. And here, for the purposes of time, I'm again using a simulator backend, which is the IBM Q Custom Simulator, but that will be executed on the IBM server. And you can then construct the VQE program. The VQE program you can simply import from the runtime module, which is part of Qiskit Nature. A quick disclaimer, this will soon be renamed to VQE client, but this hasn't happened yet. But with it being called VQE program, you can simply initialize it by passing in the ansatz that we have constructed before. You need to pass in an optimizer, which is this dictionary here at the top, where you can set the type of optimizer that you want to use, as well as the maximum number of iterations. You can specify the initial point for the optimizer. Here I'm simply using a random vector of numbers. You set the provider that we just imported. You set the backend that we just imported. You specify the number of shots, which is the number of times that you evaluate each expectation value in order to get the mean. And you can apply measurement error mitigation if you want to do that. Here, we're actually not, this may not be relevant for this specific example, but for the purposes of completeness, I'm also showing this argument here. And now that we have constructed this runtime BQE, you can actually just pass that into the ground state eigensolver in the same fashion that we constructed it with the factory that we had before. And you can then, again, solve this problem by calling solve on this solver, and then you get the output that we had before. An interesting observation is now that you can see that the number has actually changed quite a bit. And this is due to the fact that the ansatz which we now used is not a particle conserving ansatz, which you can see by the fact that we now actually have 2.8 electrons in our system, which is not the 2 that we wanted to have. And I quickly wanted to mention this because this shows how important it is in chemistry to be very much aware of the ansatz that you're using to describe your state function, because this can lead to very, very wrong results. And that's why I also chose this example to quickly highlight this as an important aspect. With that, I have come to the end of my 30-minute presentation. Here's quickly, again, the overview of what we have available in Qiskit Nature, and we're looking forward to extending this feature set much further in the future. With that, I'd like to thank all of your attention, and I'm happy to answer any questions at the end of the full hour.
Yeah, actually, we could, I think, spend a few minutes to ask 1 to 2 questions. So
sure.
There's one question from the chat. Why second quantization form is used instead of the normal form to input the classical values?
So that's a very good question. So second quantization is a very natural way for us to work in, because it allows us to do what I mentioned before, that we can map spin orbital occupation, for example, onto qubits. In first quantization, you don't have this occupation number vector that you can leverage to map onto qubits in a straightforward fashion. We're also working on first quantization approaches. I'm trying to find the slide that I used. We're also here. We're also working on first quantization applications, but these are less trivial to map into the qubit space, and that's why for now we're using second quantization.
Thank you for the answer. So there's no other chat, another question in chat, but I have one question. A very simple question. What kind of problem can Qiskit Nature solve apart from this electronic structure problem you have shown?
So apart from the electronic structure problem, we can also solve vibrational structure problems, which deal with the motion of your nuclei in your molecule. This is done via the vibrational spectrum calculations. We can also look for excited states rather than just ground state calculations. And we also recently added a protein sampling module, which allows you to do protein sampling calculations. And as part of Qiskit Nature 0.3, which we hope to be releasing this quarter, there will also be a lattice simulation model. So that allows you to simulate Fermi-Hubbard models and other systems like that.
That's great. Looking forward to the new 0.3.0 release soon. Thank you very much, Max.
You're
so
welcome.
Next up, we will have Julien Gacon to talk about the Qiskit finance modules. And Julien is a PhD candidate working jointly with the Quantum Technology Group at IBM Research Zurich and the Computational Quantum Science Lab at EPFL, Lausanne. His current research focuses on closing the gap of quantum algorithms and near-term quantum devices on both the algorithmic and circuit level. Prior to this position, he worked on the open science software of Qiskit and continues developing the core and application packages during his research. And he received a BSc and MSc degree in computational science and engineering from ETH Zurich, just like Max. And during his studies, he focused on the numerical simulation techniques and specialized in quantum simulation and computing and astrophysics. So today, Julien is going to talk to us about how Qiskit Finance can solve some interesting finance problems using quantum computing. So Julien, the floor is yours.
All right, thanks for the introduction, Julien. So hi everyone, I'm Julien. and I'm happy to talk to you today about Qiskit Finance and what applications you can already today solve with it. Right, so before we start this presentation, I quickly want to take a minute and ask, I think, one of the most important questions that everybody should ask before you start well, investing time and money into a program like quantum computing. And that question is simply, why do we care about applying quantum computing for finance problems? And to answer this question, I've picked two example applications that appear frequently in finance. So the first one is an optimization problem. Optimization problems can, for instance, be portfolio optimizations, where you have a collection of assets and you want to select these assets that maximize the return, but at the same time minimize the risk. And it turns out that these optimization problems can be formulated as quadratic programs, which are very well studied classically, and they're very difficult to solve. And with a quantum computer, there are two possible approaches with which we hope to improve these algorithms. The one kind of algorithms are the ones that we can run in the near term with devices that we have today and in the next couple of years. And these are variational algorithms. So these are algorithms like the variational quantum eigensolver, which have a classical and a quantum processor. But these are heuristic algorithms. So it very much depends on the problem that you want to solve and on the models that you have. But there's no speed up that we can prove here. On the other hand, if we look into the future and we might get fault-tolerant quantum computers, then there are algorithms based on Grover search, like Grover adaptive search, where we can show that we can expect a quadratic speedup. The second application are estimation problems, as for instance, option pricing. These problems mostly rely on Monte Carlo simulations, and in particular, if the function that you want to estimate is a difficult function, then classical computers only have a very slow conversions with these Monte Carlo simulations. And there's a quantum algorithm called the quantum amplitude estimation algorithm, with which we can also show that we can expect a quadratic speedup. And today we'll talk about both these application problems and show you how you can solve them today with Qiskit. Before we dive into that, I'd like to give a short overview on what Qiskit Finance is and what submodules it contains. So it mimics these two branches of applications that you've already seen now. And there's an application submodule, which contains tools to solve optimization problems like portfolio optimization, and an estimation submodule, which gives you the tools to solve option pricing problems like the European call option or fixed income pricing, for those who know what that means. On top of that, we also have the submodules containing circuits and tools to build these quantum circuits that you need to run these algorithms. And we have a submodule for data providers where you can load random data, or you can even load historical stock market data to test your algorithms. All right, that being said, let's dive into solving problems. The first thing that we're looking at is portfolio optimization. And in portfolio optimization, we have a collection of assets that are modeled by a probability distribution. And our task now is to find the subset of these assets that maximize our return, but at the same time minimize our risk. Why would you not include all the assets to maximize the return? Well, some of these assets might have a very strong volatility, meaning that they might give you a very high return, but also might give you a very, very low return. So it might be favorable to not take this asset into your portfolio, but rather choose one which has a mediocre return, but at the same time has a very low volatility. So you can be sure that it returns you something. And yeah, as I said, now the task is how can we find these assets that maximize the return, but at the same time have a very small risk. To answer that question, we first need to know how we model these assets. So usually these assets are modeled with a so-called multivariate probability distribution. And for example, there's the so-called multivariate normal distribution, which we denote by this uppercase vector x. And that vector, or this probability distribution, is defined via a vector of means and via a so-called covariance matrix. Now we can have a look at what these values are and how they characterize the distribution that we have at hand. So the vector mu of means is nothing but the expected value of a single variable. So in this case, where we have 4 assets, the first asset has a expected return or a mean value that's here. The second asset has this expected return, and so on. The covariance matrix, called uppercase sigma, tells us how, first of all, how does one asset vary, and what can we tell if we know the value of one asset, what can we say about the value of other assets, or if we can say something about it. So this is a matrix here colored. So we have dark values for high values and light yellow value colors for low values. And here in this diagonal, you have the variance of the assets. So this would be the variance of asset 1, the variance of asset 2. And on the off diagonals, you have the correlations between the assets. So for instance, between asset 3 and 4, you have a negative correlation, meaning that if asset 3 has a high value, then asset 4 is likely to have a low value. You can also have a positive correlation, meaning that if asset 2 has a high value, then asset 4 also likely has a high value. Or you can have very low or no correlations, meaning that if we know something about asset 1, we cannot really say anything about asset 4. How did we know this? Let's formulate our task. So we want to find the vector x star, which are the indices of the assets that maximize the return and minimize the risk. Or if you put it into a formula, we're looking for the maximum of the return minus some risk factor times the risk. And this factor Q is often also referred to as the risk appetite of the investor. And here we write that x is a binary vector. So the elements of x can be either 0 or 1. 0 for we don't take this asset into a portfolio, and 1 for we're taking this asset in our portfolio. Now, before we can solve this problem, we need to define what we mean by the risk, because there are many different definitions of what we mean by that. For instance, one simple definition that we'll use today is that we define the risk as the variance of the joint distribution, meaning that the risk is just a measure of the volatility of our entire portfolio. There are other metrics, as for instance, the value at risk or the conditional value at risk, but today we'll focus just on the variance. If we now assume a normal distribution, then we can write the return as the expected value of the vector that is our assets times the probability distribution minus the variance of that. And if we assume a normal multivariate normal distribution, then we can rewrite this as a multiplication of the vector x, which is our selection of assets, times the vector of means, minus x times sigma times x. And this formulation here is nothing but a quadratic program, because here on the left side, we have a linear part, which is linear in the vector that we look for. And on the right side, we have a quadratic part. These quadratic programs are very well studied, and we can solve them with Qiskit or with classical algorithms. So to start, let's define an example quadratic program. Here, we define our vector mu as this array with 3 elements, and we can choose whatever metric of money we want. So maybe you can just say we use dollars. So here we can say that for the asset 1, we expect a return of $2.5, 4.2 for the second one, and 1 for the third one. And this here describes the covariance matrix. In quadratic programs, you can add constraints, as for instance, a budget constraint that we add here, which means that we have 3 assets, but we only want to select 2 of them. And lastly, we define our risk factor, which here we set to 0.7. Usually this is a number between 0 and 1. In Qiskit, we have the portfolio optimization application, which we can use to construct the quadratic program that we want to solve. So we can just import this from Qiskit finance.applications.optimization, because this is an optimization problem. And we feed it the definition of our problem. So we give it the expected returns vector, give it covariance matrix, the risk factor, and the budget. Now that we have it, we can ask it to convert this input into a quadratic program that we can solve. And here we can just print the quadratic program. And this is a standard representation that's also very well known in the classical optimization community. Now, before we solve it with a quantum algorithm, let's quickly solve it with a classical algorithm. This is very well feasible because we only have a very small problem with 3 assets. So we can import a classical optimization algorithm called the CPLEX optimizer, which is an IBM algorithm. And since it's an optimization algorithm, it doesn't live in Qiskit Finance, but it lives in Qiskit optimization. So Qiskit Finance is built, you see that Qiskit Finance is built upon the tools that Qiskit already provides. So we can define our optimizer just by instantiating the CPLEX optimizer, and then we can feed it the quadratic program that we got out of the portfolio optimization application. And then we can just ask it to solve this problem. And as a result, it shows us that the optimal value is minus 5.3. We don't care about that too much. What we care more about is the optimal value. So here gives us the optimal vector to be 1, 1, 0, meaning that we include asset 1 and asset 2 in our portfolio and discard asset 3. You can see that here, actually, we only selected 2 of the 3 assets, also because we have the budget constraint. Note that quadratic programs are a very difficult problem, and here we could easily solve it with the classical machine, but with a classical algorithm. But if we have thousands of variables, then classical algorithms can run into big problems. Before we solve this now with a quantum algorithm, let's quickly recap the variational quantum eigensolver, because that's the algorithm that we're going to use. So given that you're given an Hamiltonian H, the goal of the variational quantum eigensolver, or VQE for short, is to find the ground state psi of this Hamiltonian. And the idea here is that you choose a model, which we call phi of theta, where you can tune these parameters theta. And you want to approximate the ground state psi with this model. And how you can do that is that you know that the exact ground state psi will minimize the energy. So the best parameters that you can find so that the energy for your state phi is minimal, this is going to be your best approximation to the ground state. So to find the best parameters, all you have to do is you have to minimize the energy, which is just the expectation value of the Hamiltonian given your model. Of course, this strongly depends on the ansatz that you have and how well the ansatz can approximate the actual ground state. DBQE is then implemented as a feedback loop between a classical processor and a quantum processor, where the classical processor does what it can do best. It optimizes the values, as in it takes the function value and suggests new values for the parameters. And the quantum processor does what is very difficult for the classical one, which is calculating the expectation value of the Hamiltonian. Now, DBQE is very interesting in the context of optimization problems because we can reformulate this quadratic program as a ground state search. And we do that by taking our initial quadratic program that you see here on the left, which is defined on binary variables. So maybe the solution is 0, 1, 0, 0 here. And we first map these x, which live in 0 and 1, to spin variables by this transformation that you can see here. And then we map 0 to 1 and 1 to minus 1. And then our solution for instance, looks like 1, minus 1, 1, 1. Now that we have the spin variables, we can just replace each variable by a poly Z matrix or by a poly Z operator and obtain a Hamiltonian whose ground state is the same as the optimal solution. And with that, we can now find the ground state of this Hamiltonian here. And in the end, we obtain the solution to our quadratic program. More on that you can look up in the paper that I've linked here below, because that might have been a bit fast. So before we really solve it, I wanted to give a quick overview on how the workflow in Qiskit looks like so that you can keep the overview. What we've seen already is that we can plug the means, and so the definition of our multivariate distribution, the means and the covariance matrix sigma and the risk factor into Qiskit Finance's portfolio optimization application. And then we can ask that one to spit us out a quadratic program that we can solve. Before we solve this, so with the gray box, we solved that with a classical algorithm, but now we want to use a quantum algorithm. And the minimum eigenoptimizer that you can see here takes care of the transformation of the quadratic program to a Hamiltonian. And then it needs some quantum algorithm subroutine that finds the ground state of this Hamiltonian. And for this, we use DBQE. So we give DBQE an ansatz and an optimizer and plug it into this minimum eigenoptimizer, which can then take in the quadratic program and give us back the result. To actually run this, we'll first need to select the simulator with Qiskit. So we will use a shot-based simulator from Qiskit Air and an ansatz. We will use an ansatz that is from the Qiskit circuit library and is called the real amplitudes ansatz. It's called that because the circuit that is this ansatz here can only produce states where the amplitudes are real. That's not a problem for us. Actually, that's what we want because we know that our Hamiltonian is diagonal and the ground state will have only real amplitudes. So by already selecting an ansatz that reflects this, we have less degrees of freedom, and this is ideally better to optimize. Now that we have this defined, we can import the VQE from Qiskit algorithms and import some optimizer. We use an optimizer called the SLSQP. That's not so important, but it's a stochastic optimizer. Then we also need the minimum eigen optimizer, which was the gray box in the diagram before. And we import this from Qiskit optimization. Now we can define our VQE by giving it the ansatz and the optimizer and the simulator that we want to use to evaluate the circuits and plug that into the minimum eigen optimizer. Now, just like with the classical algorithm before, we can just ask this minimum eigen optimizer now to take in the quadratic program. It will do the transformation to the Ising Hamiltonian itself, solve it, and do the transformation back to the binary variables. And if we now look at the result, we can see that we get the same result. And again, we should select assets 1 and 2. Now note that the performance here strongly depends on the optimizer that you use and the ansatz that you select. So you always have to make sure that your ansatz is powerful enough so that it can reflect the ground state of the system, and that the optimizer is also good enough so that they can find the minimum. So you might have heard about Qiskit Runtime, which is this environment, which is an environment that we provide, where you can drastically speed up iterative algorithms like the variational quantum eigensolver. So whereas previously, if you wanted to execute an algorithm and send circuits to the actual quantum computer, you had to create a job locally on your laptop or on your machine, send them to the IBM cloud, from there send them to the quantum backends, where they wait until it's their turn. Then they come back to the cloud, and then they come back to your computer, which is a process which inevitably takes a lot of time. You can just move the entire algorithm onto the cloud. So instead of going through all these 3 steps in every iteration, you just wait, you queue once until it's your turn for the entire algorithm. And then you have a quick access from the cloud directly to the quantum processor. And then once the whole algorithm is done, you get the results back. And this can, for iterative algorithms like the variational quantum eigensolver, can speed up your algorithm by several hours. So to leverage this, we can almost use the exact same structure as before. The only thing that we change is that we replace the VQE by the VQE client, which has a direct access to the quantum computer. So to look at the changes that we have into the code, we can have a look at this slide. And there's really not much that you have to change. The only thing that you have to change is that instead of the VQE that you imported from Qiskit algorithms, you import the VQE program, which is soon to be called the VQE client, from Qiskit optimization. You give it almost the same input arguments, except that instead of the quantum instance already simulated that you gave it before, you now give it the provider and the backend which you want to use to execute your circuits. All right. So that being done, let's talk about option pricing. So a financial option is the right to buy or to sell an asset for a certain price in a certain time window. And going from this definition to a very practical example, let's have a look at the so-called European call option, which is probably the simplest option that exists. So in the European call option, you have one single asset, and at a fixed maturity time t, you can buy this asset for an agreed upon so-called strike price k. So if we look at this in the diagram, you have your asset, whose price develops here with this blue line. And now at this time, I'm telling you, okay, at the maturity time t, you can buy this asset for price k. This is interesting because, of course, we don't know how exactly this asset will develop. So as time goes by and the market evolves, the asset will have a final so-called spot price, so the actual price as of t, and this might be higher or lower than the price that we agreed upon. And depending on whether it's high or lower, either I or you can make money with that. So the question that we try to solve with option pricing is essentially, is it worth it to buy this option or not? And we answer this question by using the so-called payoff function. So the payoff function tells us, depending on the spot price and the strike price, what is the gain, the financial gain that you can get. So if the asset, so the real price of the asset S is below the strike price, the asset lost value. And if you would buy it for the strike price K, then you would buy the asset under market value. Of course, you wouldn't do that. So you're just not buying it, which is why the payoff function here is flat. On the other hand, if the asset gained value, you can buy it under market value and you get a payoff, which is linear, which is this part of the function here. So now to put it in math, the quantity that we want to estimate is the payoff, which is the expected value of this piecewise linear function. And the way that this is usually solved is by means of a Monte Carlo estimation, where you take a large number of samples of this function and then you average it, which gives you a good estimate of the expected value. The Monte Carlo estimation here, or the error of the Monte Carlo estimation here, converges as 1 over the square root of the number of samples, which can be quite slow if the function here is not as easy as in this particular example, but more difficult. And the question here is now, can we do better with the quantum algorithm? To answer this question, let's have a look at the so-called quantum amplitude estimation algorithm. The idea here is that given an operator called uppercase A, that if we apply to the state 0, gives us back a state psi, which consists of a so-called bad state psi 0 and a good state psi 1. The task is to find the probability to measure this good state, or to find the amplitude of this good state psi 1. And this problem has been formulated and solved in the year 2000. And the idea here and this algorithm is that you take this operator A, from it you construct an operator Q, whose eigenvalues depend on the amplitude A. Since this is a unitary operator, the eigenvalue is a complex phase, and you can estimate this phase with the phase estimation algorithm. And once you have that, you can recover the amplitude from the phase that you estimated. This algorithm is implemented in Qiskit, and you can import it from there and play with it. This is a very crucial algorithm, and especially in the last 2 years, there have been many developments and improvement on this algorithm. More information on that you can find in the amplitude estimation tutorials on Qiskit Finance. Going back to our option pricing example, we wanted to calculate this expected value, and we had the convergence of 1 over the square root of m, and this is what we wanted to improve. Turns out that amplitude estimation has a better convergence, a quadratically better convergence to be precise, of 1 over the number of samples. So the question is now, can we connect this expected value and amplitude estimation? Or can we write this amplitude A as the expected value of some function? And if we can do that, then we can leverage this quadratic or this better convergence and obtain a quadratic speedup with a quantum algorithm. And it turns out that yes, this is possible. And we do that by using the definition of the expected value, writing it as an integral, and then doing a numeric integration. More information on that, for instance, you can have a look at this paper that I've linked here. The structure of these A operators usually looks like that. So you have a blue part here, which loads the probability distribution of our assets, and you have this yellow part, which is the payoff function. In our case, it's this piecewise linear function that you've seen before. And the circuit that implements this operator usually looks like that. So you have first a circuit block which loads the probability distribution, and then you have a block which implements a payoff function. And both these circuits are implemented in Qiskit Finance's circuit library. So for instance, for the European call pricing objective, you can import the same name, the circuit with the same name from the circuit library. And for the normal distribution, you can, for the probability distribution, you can import several distributions, like for instance, the log normal one, which is what we are going to use here, but there are also other ones. The accuracy of this approximation firstly depends on the approximation of the integral that we have. So how well can our integral, our amplitude A, represent the actual expected value? And this depends on the number of qubits that we use to represent the probability distribution. And here we'll just use 3, which gives us 8 terms in the sum. If we use the Black-Scholes model to model the asset, then we know that at the strike time t, the asset can be described by a log normal distribution. I'm not going to dive into details of that. You can have a look at that paper. But here we just need to define the strike price that we agreed upon and the maturity date. And then we can do some math and we obtain the parameters for the log normal distribution. Once we have these, we can plug these into the log normal distribution object for Qiskit, give it the number of qubits that we use to model it, the mu and sigma, and then it can load the distribution for us. Distribution loading is a very important point if you want to solve practical problems on a quantum computer, because you have to make sure that every step of your algorithm is efficient, not just final amplitude estimation, but every bit, every piece that you use to get there. And more details on efficient loading you can find in this paper that I've linked here. Okay, now we have everything to define our European call option. And again, we'll have a quick overview on how this works in Qiskit. So we can define our probability distribution using the maturity date and the asset model. So this is the parameters of the log normal distribution, and use Qiskit to get a circuit to implement this distribution. Then we can use that and the strike price to use the application. And this gives us an estimation problem, which is the input to the amplitude estimation algorithm. So similarly as before, the optimization algorithms solve the quadratic program, the amplitude estimation algorithms solve an estimation problem. All right. So the application, we can again import that from Qiskit finance.applications, and we give it the number of qubits that we want to model the probability distribution with, the strike price. We give it an approximation factor for this piecewise linear payout function, but you don't have to care about that too much right now, and the probability distribution. Then we can convert this into an estimation problem by calling toEstimationProblem. And now before we solve this, we can have a look at the A operator. And if we draw it, you can see that here the first block is this is called P of X, which is the loading of the probabilities. And the second block is called F, which is the payout function. So you can see this is exactly what we discussed before. I mentioned before that there are many flavors of this amplitude estimation algorithm, and here in this tutorial we'll use one of the fastest ones that we have right now, which is called iterative amplitude estimation. And this algorithm, we give it a final target accuracy, and we give it the size of or the confidence interval that we want, so how sure we want to be of our final result. And we reach the same simulator that we had before. Now that we have that, we can solve the problem just by calling the estimate method on the amplitude estimation algorithm and giving it the problem. And then the result contains the estimation for the expected value, which is here 0.16, which means that we can expect to get a payoff of $0.16. And the confidence interval that we have is here. So with a 95% probability, we expect our estimate to be within this interval. So in practice, you have to pay something for the option. And if this is the money that you have to pay for the option, then we can expect on average to not gain anything. So both you, the buyer, and I, the seller, have a fair gain. All right, so there are many more options and many more constellations. Here we look at the European call option, which was the simplest one, and this is actually one that you can solve analytically, classically. But there are many more options like American options or a path-dependent options or autocallables, which are much more difficult to calculate classically and where we hope that quantum computers can help us. All right, to wrap this up, we have seen two possible applications of quantum computing in finance. One branch was optimization problems, as for instance, portfolio optimization, where we've seen that we can map problems like portfolio optimizations to quadratic programs, to Ising Hamiltonians, and then use algorithms that we have today, like VQE, to solve them, but a heuristic. So we have to make sure that we use a good model and a good optimizer. Second branch of applications are estimation problems, as for instance option pricing, where we have seen that quantum algorithms can give us a quadratic speedup in the future. All right, thanks a lot for your attention, and I have linked more references here in case you're interested or want to read more.
Thank you very much, Julien. We have a lot of questions in the chat, and I have answered some of them, but I can pick up one or two that we can highlight since we're already over time. So one participant asked, the Grover adaptive search implementation in Qiskit has a parameter called number of iterations. Can you explain how to select the value of this parameter that optimally for a certain Kubo problem?
I think that's a very detailed question on the implementation of Qiskit. So it would probably be best to have a look at the documentation, since I don't know the documentation by heart. And if you don't find the answer there, then I encourage you to either post an issue on Qiskit Finance or Qiskit Optimization, or post a question in the Slack channel. Then there we have time to have a look at it.
Sure. And another participant asked, for the optimization purposes, can Grover adaptive search be considered to be better than the quantum annulers?
So this depends on, so annealing in general can also have a quadratic speedup. However, the problem with annealing is that we usually have to choose exponentially small annealing times. I think this is not a problem that the Grover adaptive search has. So in the case that we cannot circumvent the exponentially small annealing time, then it would have an advantage over that.
Okay, great. So one more question. The portfolio optimization problem can usually be mapped to an Ising spin glass Hamiltonian. And is there any particular reason for choosing VQE over QAOA for this problem?
So QAOA is just a flavor of VQE. So the QAOA algorithm is just VQE, but with a certain ansatz, which depends on the problem. So you can also use QAOA to solve that. One thing to keep in mind with QAOA is that it's based on a Schottlerization, which means that it can lead to very deep circuits. So in QAOA, to improve the accuracy, you usually increase the order, which increases the circuit depth, and in real devices that can become a problem. On VQE, in a general VQE, where you can select any ansatz, you don't have this restriction, and you might find a better Hamiltonian which suits, which you can implement on the real devices. But QAOA is also definitely a valid option, and you can also solve this with QAOA. That's a good question.
Yeah, thanks for the explanation. So I just want to ask the same question I asked Max. What kind of problems that Qiskit Finance can solve apart from the two problems that you have, so portfolio optimization and option pricing?
There are many more option pricing alternatives implemented in Qiskit, also ones that are classically a bit more difficult. And I encourage everyone to have a look at the finance tutorials. I think we have about 11 of them, which is quite a lot. So here I only covered 2 of these 11 tutorials.
Okay, great. Then with that, I think we can close this session soon. Yeah, thank you everyone for joining us today. And I just want to remind you that we have an upcoming IBM Quantum Challenge from October 27th to November 5th. So if you want to get to know more about these Qiskit application modules and want to put them into the practice and try to do some coding, online quantum programming exercise, that would be the best chance for you. So I'm going to send a link in the chat so that you can register. So thank you very much and hope to see you soon. Remember to subscribe to Qiskit YouTube channel if you want to hear more quality content like this one in the future. Thank you.